Okay, let's just jump right in. 9 out of 10 students, seriously, a massive 90%, get binary and denary conversion completely wrong in the exact same way. And the worst part? It quietly costs them their grade. Let's actually walk through this exact mistake right now so you can make sure you don't fall into the same trap in the exam hall. You know how it is. Exam pressure hits, the clock is ticking down, and students think, hey, I know my base 2 numbers, right? So they rush. And because they're rushing, they confidently write down totally corrupted data sets, all because of one incredibly simple, completely avoidable oversight. Just consider this scenario for a second. Can you spot why so many people fail this specific conversion? All right, let's break down this 10-second fail. The student is trying to convert the denary number 155 into binary. But look at what happens when they write out their powers of 2 from memory. They start strong, 128, 64, 32, 16, and then boom, they jump straight to 4. They completely miss the 8 column. Because of that single little memory slip, literally every subsequent bit is misaligned. They end up writing 1001011 when the correct answer is actually 1001111. Just one missing column, and the computer is suddenly reading a completely different instruction.
Which brings us to Section 1, Foundation, how binary actually works.
To make sure a mistake like that becomes absolutely impossible for you to make, we're going to rewind a bit. We need to build this concept correctly from the ground up. Instead of just purely memorizing numbers, let's understand what the machine is literally doing. So, binary is a system using just 2 states, 1 and 0. Inside the hardware, these are just physical transistors that are either on or off, holding an electric charge or holding no charge. These tiny individual digits, or bits, are organized into groups of 8, and that 8-bit group is called a byte. Every fact, every image, every single text character is stored inside the computer as these precise 8-bit values. To really visualize how a byte behaves, let's use a brilliant practical activity from our source material. I want you to imagine 8 students sitting in a row of chairs at the front of a classroom. These 8 chairs represent the 8 bits in a single byte. We are going to mentally act out how binary counting actually physically moves. Here are the physical rules for our 8-chair byte. If a student is sitting down, that's a 0. If they stand up, that's a 1. The chair on the far right represents the units column. Now, what's super interesting here is that the student in that far right chair actually has the most work to do. Every single time we count up by 1, that specific student has to change their position. And this perfectly illustrates the carry mechanism in computing. Think about it. If you're a student in this row and you're sitting down, your rule is easy. Just stand up. You've gone from 0 to 1. But if you're already standing up, meaning your bit is maxed out at 1, you have to turn, nod to the person on your left, and sit back down to 0. That physical nod, that is the carry signal. The person who receives that nod then follows the exact same rules. This whole cascade of standing, nodding, and sitting mimics exactly how binary logic gates process addition, and we didn't even have to do any complex math to understand it. All right, moving on to Section 2, the right conversion method. Let's see how our physical analogy of bits filling up translates into the mechanical methodology you absolutely have to use for the IGCSE exam. Let's start with converting binary to denary. The golden rule here, always map your bits to the standard 8-bit grid. You just write out your place values from left to right, 128, 64, 32, 16, 8, 4, 2, 1. Each value is exactly half of the one before it. Once your grid is set, slot the binary number underneath it. Then you literally just multiply the active bits, the ones, by their column value and sum them up. So if we have a 1 under the 16, an 8, a 2, and a 1, well, 16 plus 8 plus 2 plus 1 is 27. It's clean, it's highly visual, and honestly, it leaves 0 room for error. But converting the other way, denary to binary, is where people fall into that trap we talked about earlier. You will constantly see flawed methods where students try to do the division process in their heads too early, or they kind of just guess and build the number randomly. Don't do that. The only foolproof exam method is methodical subtraction, and you always start from the largest possible value on the left. Let's do a deep dive with a worked example. We want to convert 155 to binary, so we write out our 8-bit grid. Start at the far left, 128. Is 128 smaller than or equal to 155? Yep. So we place a 1 in that column and subtract 128 from 155, which leave us with 27. Move to the next column, 64. Is 64 smaller than 27? Nope. Put a 0. Next is 32, still too big. Put a 0. Next is 16. 16 fits into 27. Put a 1. Subtract 16 from 27, leaving 11. Move to the 8. It fits, so put a 1. 11 minus 8 leaves 3. Next is 4. Too big. Put a 0. Move to 2. It fits. Put a 1. 3 minus 2 leaves 1. And finally, that 1 column gets a 1, leaving us with exactly 0. By strictly subtracting from left to right, we guarantee we check every single column. It literally makes it impossible to accidentally skip the 8 column like our student did at the beginning. Okay, section 3. Make it stick. Spot the error challenge. Let's put this into practice together. There is a very specific, hidden detail in these grid setups that examiners actively hunt for, and if you miss it, you are throwing away marks. I'm going to give you a fresh, flawed exam answer. There is one single point of failure in their logic. You have 10 seconds. Can you spot exactly where they messed up? Okay, time's up. Did you catch it? The student mapped the binary number 1110101 to the grid. They got the 128, 64, and 32 right, but wait, look at the fourth column. Instead of the number 16, they just randomly threw a denary 10 in there and then confidently continued with 8, 4, 2, 1. They completely broke the power of 2 rule. Remember, every column must be exactly double the column to its right. 16 is double 8. 32 is double 16. By slipping a standard number 10 into a binary grid, they corrupted the entire calculation. Always, always double-check your grid headers before you start doing the actual math. Which leads us perfectly into section 4. IGCSE strategy and success. So we've got the technical knowledge locked down. Now let's talk exam strategy. How do we translate everything we just learned into the exact phrasing that Cambridge examiners actually give marks for? Well, it's all about the command words. The IGCSE mark scheme is incredibly strict about this. If a question asks you to state the binary equivalent of a number, they literally just want the concise final 8-bit answer. No extra fluff needed. But if the command word is calculate or show, just writing down the correct final answer will not get you full marks. You have to actually write out the full mechanical process, your grid, your subtractions, your additions, right there on the exam paper. And here is why showing your work is an absolute game changer. Method marks. Let's say you're super stressed, time is running out, and you make a tiny, silly arithmetic error in your final subtraction, which messes up the very last bit. If you only wrote the final answer, you get 0. But if the examiner can see your grid and your subtraction steps, they will actually award you points for demonstrating the correct method. You literally guarantee yourself marks even if your math is slightly off. Oh, and one more thing. Always apply your calculations to the specific nouns in the scenario. Whether they're talking about sensor data, sound files, or network packets, context is absolutely key. Also, a quick side note while we're talking about data entry. Examiners love testing 2 specific terms alongside binary data: validation and verification. Do not mix these up. Validation is an automated check by the computer to ensure data is sensible and allowable, like, making sure an entered month is between 1 and 12. Verification, on the other hand, is checking that the data entered perfectly matches the original source document, which is often done by just typing the data in twice. Just a quick tip to keep those 2 straight. If you found this breakdown helpful and you want to actually understand these concepts instead of just memorizing a textbook, make sure to subscribe to our YouTube channel, Ace the Exams. The handle is @acetheexams_IGCSE. We're building a really great community dedicated to crushing these Cambridge exams through clear visual learning, and we'd love to have you. All right, so we have successfully mastered base 2 conversions, and we know exactly how the computer thinks in ones and zeros. But I want to leave you with a bit of a provocative question. Reading strings of millions of ones and zeros is literally impossible for human programmers. So how do computer systems compress massive, massive blocks of these bits into a clean, human-readable shorthand? Well, the answer lies in base 16. And trust me, you are definitely going to want to decode that next layer of digital language in our next explainer on hexadecimal conversions. Catch you in the next one.